Yeah. Okay. I'm Dylan Hauenstein. Today we're presenting on specialized software and equipment for high-speed cameras. As background, Bruce Hauenstein and I work for Gravic, a computer software firm in Malvern, Pennsylvania. We have an electro-optics lab called Gravic Labs, where we do a lot of our work. Our co-author, Steve Connard, has been very helpful with testing our experimental software. Our motivation, or next slide. Our motivation for working on high-speed camera software and hardware resulted because of our interest in high time resolution observations of transient and high cadence events, such as occultations. We're interested in the occulted star as much as the occulter. To achieve our goals, we needed multiple high quantum efficiency, low read noise, fast readout cameras in an array. We also need precise timing and the ability to record for extended periods of time. Next slide. Okay. Yeah. Next slide. Yeah. Some of the cameras we have acquired are shown in the pictures. The larger photometrics cascade cameras on the left and the 3 Andor Izon cameras on the right use EMCCD detectors. EMCCDs have an additional set of registers on chip which multiply the photoelectrons prior to readout. Next slide. These two charts from the camera manufacturers show the incredible capability of the EMCCD cameras. On the left, readout noise can be reduced to far less than 1 electron per pixel. On the right, the top curve, which is not really visible here, is the quantum efficiency of a back illuminated EMCCD chip. It shows that far more photons are collected per unit of telescope area. Next slide. We wanted a simple piece of software which would provide full camera control of the EMCCD features, a live view of the star while recording, support for multiple cameras, and the ability to record for long periods of time with precise frame timing and no data loss. We also wanted graceful recovery from equipment failures, such as the PC crashing. Next slide. We looked at the available software: Micromanager, WinFlare, RSImage, ACQ4, Andor Solus, and many others, but none of them had the features we needed. Whether it was triggering, timestamping, high-speed acquisition, open-ended recording, live view, multiple camera support, a usable data format, reliability, any number of things, they all lacked something important. So we decided to write our own software package, which we call PVCam Recorder. Next slide. On the left, the architecture diagram shows up to 8 cameras may be controlled. In practice, though, a typical PC can only handle 2 or 3. The GPS device synchronizes the PC's time, and its 1 PPS pulse is used for triggering the cameras. Our new software, PVCam Recorder, grabs the data from the camera and produces an uncompressed binary file with microsecond timestamps for each frame. We wrote a converter program to take our raw binary file and produce a Tanger 3 compatible ADV file. Tanger 3 is able to produce or to process the 16-bit data and timestamps to produce the light curve. One of the main issues with occultation timing is, of course, next slide. Yeah. One of the main issues with occultation timing is, of course, precise timing of the event. We decided to use the camera's external trigger input and then experimented with several ways of initiating the trigger. The simplest approach uses a camera trigger interface card we developed. and a thumb switch to turn off the pulses. When the thumb switch is depressed, or was released, the very next pulse, whose rising edge, will trigger the camera and start the acquisition sequence. The PC clock is used to get the start time and must be synchronized to within 500 milliseconds of the true time. When the program gets the time from the PC clock, it knows that the next 1 pulse per second pulse is the start of the nearest second. Getting a little feedback. Next slide. A screenshot of the user interface is shown. It's a work in progress, but even at this stage, gives us control over most of the important features of the camera. The image on the right is a separate window that shows a live view of the target. Slide. With our new software, we were able to record the lossless data stream in a format that couldn't be corrupted by equipment failures, but we ran into a new problem. We needed a software package to analyze the 16-bit data. We tried converting to FITS, AVI, SIR, and tried programs such as AIP for Win, LuCam, MetaCurve, and LeeMovie. Unfortunately, none of them fully supported our 16-bit data. We really wanted to use an Iota proven package, so we contacted Hristo Pavlov, the creator of Tangra. He was very fast about fixing some of the problems we found. We're thrilled to say we can now convert our data into the ADE format used by Tangra. Next slide. To verify the operation of the system, we recorded an LED blinking with a 1 pulse per second GPS signal in our lab. The comparison was between a SuperCircuits camera feeding into an Iota VTI and our new software running a Photometrics Cascade 128 EMCCD camera at 200 frames per second. Next slide. It's not showing up super well, but the Tangra light curve for the SuperCircuits camera is on the right above, and the pulses are 100 milliseconds wide. They're rounded on the top because of the 30 frames per second sample rate. The frame shown corresponds to the vertical red line at the start of the first pulse. It appears about 13 milliseconds after the start of the second. Next slide. Because of the frames per second, it notices that the thing has started blinking 13 milliseconds late. Yeah. In contrast, here's the light curve of the EMCCD at 200 frames per second. The not too noticeable red line on the first pulse has a start time that's within 1 millisecond of the true start of that second, according to the GPS unit. The pulses are square on top as well because of the sampling rate being nearly 7 times faster. Next slide. Steve observed Regulus in preparation for the March occultation by Origine. The diagram on the left is a 64 by 64 pixel region of interest. The Tangra 3 light curve is shown on the right and has a signal to noise ratio of over 10 to 1 for each frame. Next slide. And we observed Hauenstein Iya this past Monday night. The image on the left is the full 512 by 512 frame. The star being occulted is the bright object in the center at magnitude 10.7, and the asteroid is the fainter dot to the left at magnitude 12.8. Some of the light curve at 96 frames per second is shown on the right. We had a miss. The two dips near the start are where we covered the telescope's aperture. Just as a little bit of fun. Overall, the equipment is now operational and will join the effort on Monday night. Next slide. And that's it. Thanks for listening. Yep.
Any questions?
Oh, yeah.
Would you say that the winning resistance is 14%?
No, that's the IOTA VTI. That's 13 milliseconds. Yeah. Yeah, the sampling rate is effectively, yeah. Yeah. Our system was like less than a millisecond. So, yeah. Any others? Yes. They're back there.
Thank you. I would love to see it.
Wow.
Yeah. They're pretty heavy. So this is a Photometrics Cascade 512B. We can typically get about 200, 250 frames a second out of these.
What were the parts that we had to make for this?
Do you have one of those boards?
So the front end.
Oh, yeah. We made this front plate for the 2-inch. Yeah.
Inside.
What about it?
Well, you can fit a filter in either 2
Yeah.
inch or 1 1/4.
I got it. Yep. And this is a Photometrics Cascade 28. And static. We can get up to about 3,000 frames per second out of these, and run at around 1,000, because when you go up higher, the region of interest is small enough that it's really annoying. 24 by 24 micron. Okay.
Excuse me. So we bought these two off of eBay, and a lot of them are used in the microscope and labs in the biology field, and in particular, when the lab goes out of business, sometimes people will dump them, and we've been lucky that way to get a few off of eBay for very inexpensive prices.
Yeah, do EMCCDs require special handling or calibration? I suppose so, but yeah, for the most part, they just work. Some of them, we have a set of 512Bs that have a special, do you remember what it's called? Like lumochrome coating? Lumagen coating. Yeah, which enhances the UV response. And those need to be kept out of the sun. But beyond that, nothing that I know of. Yeah. Yeah, yeah. You don't. If the power adapter has power when you plug it into the camera's dead. Yeah. You have to follow certain setup procedures, but beyond that, yeah. 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 That's another important thing. Gain aging. If you consistently run with a high EM gain, it like saturates the gain registers and they stop functioning, which can happen in as little as a couple hours if you're like truly saturating the camera. Yeah. Yeah, and as long as you're not saturating the pixels and stuff like that.